So hi everybody, my name is Massimo Grassi and I work at the University of Padova at the Department of General Psychology, and here I'm going to give you some basic facts on sound perception. Something very simple. So how do we perceive sounds? First of all, we have a sound wave which is touching our ear, the outer ear, which is the thing that you can touch with your hands. And this sound wave is setting into vibration the eardrum, and the eardrum is also setting into vibration the middle part of your ear, which includes the ossicles, which is a series of 3 bones, the uncus, the malleus, and the stapes. These 3 bones start to vibrate, and eventually the stape, which is the last bone, is pressing the inner ear, which is exactly the part that is encoding the sound, and it is placed inside your skull. Inside your skull, there is the cochlea, and this cochlea is receiving the vibration from the stape, and this cochlea is vibrating as well. The cochlea is full of receptors, which are called hair cells, that transform the mechanical vibration of the sound into a neural spike. And starting from the hair cells, we can go up to the brain and up to the auditory cortex through the auditory nerve. And the auditory cortexes, the left and right auditory cortexes, are on the left and right of your temples, so just in front of your ears. How do we encode sounds? There are 2 main things that happen at the level of the cochlea when we receive a sound. Sound is a complex wave that includes several frequencies, and these several frequencies are encoded by 2 different mechanisms. The first mechanism is called spatial encoding. Each frequencies find a peculiar place along the length of the cochlea. And in particular, the base of the cochlea is very sensitive to high frequencies, whereas the peak and the apex of the cochlea is very sensitive to low frequencies. And this is the so-called tonotopic organization of the cochlea. So the cochlea maps frequency into space. The second type of encoding that the cochlea gives to frequencies, to sound frequencies, is a temporal encoding. Hair cells tend to discharge in phase with the frequency of the incoming sound wave. So there is this one-to-one temporal connection between the frequency of the incoming sound wave and the discharging rate of the hair cell. How do we perceive sounds? Of course, at the moment we were just talking about physics and physiology, but in our head we have nothing like spikes or things, but we actually have a proper sound perception and a sensation. Generally speaking, we have 4 main sensations which are associated to sound. We can discriminate sound for pitch, so we hear sound that are very high pitch or low in pitch, something like this. Or we can perceive, for example, sounds along the loudness dimension, which is perceiving very quiet sounds or very loud sounds, okay? Or we can discriminate sounds for timbre, for example, such as when you play the same note with 2 different music instruments, so like a guitar or a piano, exactly the same pitch, exactly the same loudness, but then again, you can discriminate the 2 sounds because you are producing 2 different timbres. And of course, we can discriminate sounds for duration, although, as you might imagine, duration is a sensation that is cross-sensory in the sense that we have sensation also for visual events, for tactile events, and any other type of sensation. We, of course, are able to perceive sound in space, so we are able to tell where a sound source is. And this is mainly done because we have 2 ears. So, for example, we are good at discriminating left and right. And this is because when a sound wave is arriving to our from our right, for example, it first touches our right ear, and then just a fraction of time later, our left ear. By the same token, for example, the same sound wave first touches our right ear and then is masked and partially attenuated at the level of the left ear, so that at the level of the left ear, the sound sounds just slightly softer. And this are two indexes that give us the idea of where a sound is coming from. We also understand the vertical position of a sound, not so well, but we can. And this is done with a kind of peculiar mapping between the reflection of the sound wave at the level of our pinna and all these reflection waves and the effect that all these reflection waves have on the frequency distribution of the frequency content of the sound. In open space, we can also tell whether a sound source is close or far away, mainly by the absolute intensity of the sound source, but perhaps there are also other indexes. Grossly speaking, we divide sounds into tones and noises. Mainly, the main distinction is that tones can give a clear sensation of pitch. So, for example, if you listen to the sound of a musical instrument, the sound of a human voice, the chirping of birds, all these type of sounds can be used to create melodies very easily because they rise as very strong sensation of pitch. You can order them from low to high, for example, in pitch. In contrast, we also perceive noises, which are sounds that do not evoke such a strong sensation of pitch. So, for example, if you listen to the fan or of the air conditioning of your room, this is a noise that doesn't give you a very clear pitch sensation. Although sometimes, for example, there are some noises, like, for example, the engine of a car when you are accelerating, which might give rise to a sensation of pitch. We have limits in our perception, so we do not perceive everything in terms of sound. In terms of frequency, human beings are sensitive to frequencies from 25 to 16,000 hertz. Pretty much both limits are depending on several individual factors. The main one is age, and in particular at high frequency. When you are getting older, you lose the sensitivity for high frequencies and you become deaf to high frequency. For example, I'm already a bit deaf to high frequencies. This is starting from 40, 50 years old. The major and the most fine sensation for sounds is roughly within 5,000 hertz. So from very low frequencies to 5,000 hertz, we have the finest sensation of pitch. And in fact, if you check, for example, music is mainly composed by using frequencies that fall within the range of 25 hertz to 5,000 hertz pretty much. We have, of course, also limits for intensity. So there are sounds that are too quiet to be perceived. Our sensation of sound starts roughly at 20 micropascals for certain sound frequencies, but depending on the frequency, this number might be different. And of course, there is the other side of the coin when you are producing a sound that is too high in intensity. At that point, of course, your sound sensation changes and changes into pain sensation, because sounds sometimes can be too loud to be perceived, and actually the sound sensation is replaced by a pain sensation. So a few things now about sonification of objects. I'm now list a few things that are empirically supported and few things that are not empirically supported but are personal opinions, although perhaps kind of shared by many others. Okay, so we can use any type of sensation associated to sounds to sonify objects. So we can use pitch, loudness, timbre, duration, the spatial position as well to sonify auditory events. And we can follow, let's say, roughly speaking, two types of ideas or hypotheses for the sonification. We can follow a kind of natural mapping and associate a characteristic, a physical characteristic to a characteristic of the sound that are usually associated in nature. So, for example, I'll give you an example. In nature, large objects tend to produce low frequency sounds, and small objects tend to produce high frequency sounds. And therefore, if we want to map, for example, the size of an object and sonify the size of an object generally speaking, it is kind of natural to associate low frequency to large objects and high frequency to small objects. This is kind of natural because in nature it is like that. We can also have some arbitrary mapping, like, for example, when you associate the luminance of a light with a certain characteristic of a sound. So, for example, you might associate the luminance of a light with a sound frequency and associate high luminance with high frequency. But of course, this type of relationship is just arbitrary. It might sound reasonable, but there is no reason in nature why these two things should be associated exactly in this way. Of course, as far as sonification is concerned, this is my opinion, both natural and arbitrary mapping can be used as long as it's a good sonification. So as long as the sonification can be learned fastly, can be remembered, can be fruitfully exploited by people, as long as these characteristics are you can fulfill all these characteristics, any type of sonification is good, arbitrary or natural. Pitch is definitely the most investigated and exploited sensation as far as sonification is concerned, and this is because human beings are very good pitch detectors. We are very good at dealing with pitch in general. Is the sensation we are best at. We remember, for example, pitch very well. Imagine, for example, the first time you hear a melody, and then after months and months and months, you can still remember a melody because you can encode pitch in long-term memory very well. Okay, you might be exposed just once to a melody and then remember that melody forever and ever, because we have a very good memory for pitch. If we were listening to a series of loudnesses, for example, we wouldn't be able to remember loudnesses so well in time, okay? And plus, this pitch discrimination, pitch ability can also be improved. Think about, for example, you and a musician in comparison. In general, musicians tend to have better pitch abilities than non-musicians, and this is because practice is improving their ability to deal with pitch. So pitch perception can be improved. For example, there are no data about the possibility of improving, for example, loudness perception if you are training with loudness. And then again, there are several, some natural and some not, associations between pitch and characteristics of objects. So, for example, we saw the relationship between pitch and size, but there are also cultural tendencies to associate pitch with spatial position. So, for example, we say high in relation to a high pitch. So we use a vertical adjective that is defining a vertical position to define pitch, and we say low in pitch. And this is shared by many cultures. For example, definitely is true for, as far as I know, all the cultures in the Western culture. I don't know whether there are other cultures that encode pitch in a different way. Of course, you can also use loudness, timbre, duration, and spatial position, but there are problems here and there for each of these characteristics. They might be associated, of course, with something. I mean, you can also think about sonifying by putting together loudness and pitch and so on. So, for example, we are good at discriminating loudnesses, but we hardly remember them, and therefore loudness can be used, but has limitations. As far as timbre is concerned, in auditory perception, for example, timbre is associated to object. When you listen to a different timbre, you listen to a different sound source. So, for example, my voice and the voice of Elif, which that will talk later after me, have a different timbre, and we tend to associate strongly timbre with object. Okay. Spatial position is a nice feature that we could exploit. In particular on the horizontal plane, but also on the vertical plane. But keep in mind that, for example, if you want to have a good artificial spatial sonification of sounds, you need headphones, you need earplugs, and therefore, for example, you need a surround system around you. So, for example, this type of sonification is good, but for example, if you want to sonify something through a mobile phone and have people to listen to your sonification through the speakers of the mobile phone, of course, there is no way you can do well the spatial position of sound. And this is it. I think for this is over, and I will be ready for your question at question time. Thank you.
Okay. So thank you, Massimo, for this amazing presentation. And you actually laid the ground for me to explain how we experience product sounds in general. So my name is Elif Özcan Vieira. I'm the Director of Critical Alarms Lab at TU Delft, and I'm an Associate Professor in Sound-Driven Design. And I'm very happy to be reaching out to a completely different domain, and how we can sonify our universe is, I think, is an amazing opportunity for all of us to practice our ideas. So when we talk about product sounds, actually we talk about daily objects, and these objects are very familiar to all of us. Let's listen to a couple of sounds and remember how Massimo actually explained to us how we perceive sounds in general. This is the sound of an electric shaver, and I hear a very high-pitched sound, and it is not very loud because it's also a small object, but it does give me information that this is a very healthy machine and it's working well. And actually, the razor makers, they use sound as a tool to understand whether man or woman, they can shave by using the sound, because when the blades hit the hair, it does create a completely different, more prickly sounds than when it's just working smooth by itself. And they use it for quality control. In Philips, there are shaver ladies that listen to the sound of the product as a quality check after the end of the work line. So these sounds are important for us. But sometimes product sounds are so prominent that they become the product themselves. I'm going to play you a very famous sound that many people try to trademark it, but it is not possible. But this is the sound of a powerful and adventurous Harley-Davidson motorbike. And there it goes. And like Massimo was also describing, there's this temporal domain. There are different pitches and there are different small events. We are all able to segregate and collect all these sound events together, and all of them make out the sound that this product makes. And it is part of this engine and how it works. It's a V8 engine, right? The way it functions also gives us this nice and repetitive sound, but it is powerful. It comes from a big product. And when people are on this product, they also feel the power themselves. They feel empowered because of the sound. So the sound can also have such a side effect on the user. But sometimes sound can also be used for identifying the brand. And we did a project by designing a welcoming sound for Toyota Motors Europe. And when people when they get in their car in the morning, they switch on the car, this would be the sound that they would hear. We wanted to create a playful sound and a sound that is not tiring, because if you're a musician, you will notice that these sounds are still within the similar harmonic range, but they are a bit unpredictable. We try to create that unpredictability so that every morning you feel like you're listening to this sound all over again, because otherwise it would be very, very tiring. And if everything was very smooth and predictable, like in a music, that Massimo was saying, that when you listen to it once, it's engraved in your mind and you will never forget it. So we were trying to play with the perception here and with the help of musical theories. And sometimes sounds are also super functional for us. And I have 3 kids at home, and almost every other night I hear this dying battery sound of a toothbrush. And I know that it is not going to brush well, and I know that I have to put it on the charger, and I know it because the pitch gets lower and there is not enough energy. The product and the rotation gets slower, and therefore we hear lower pitched sounds. We use sounds as part of our lives, and we often don't notice because it's like tacit knowledge. We learn the relationship between objects and sounds. But we did a study. We asked people how similar they thought certain sounds are. So we did discover 6 distinct type of sound categories that are perceptually relevant, and we put them on 2 axes. We did a multidimensional scaling analysis, and what we found out that on dimension 1, sounds were ranging between noisiness and low frequencies. On dimension 2, loudness and sharpness were more prominent. So then there was this array of impact sounds that are, for example, high in sharpness and loudness, and alarm sounds next to that. And then we had, liquid sounds that are high in low frequencies, and they're also more noisy. And we had very, very high cyclic and air category sounds that were very high in loudness and very also much lower frequencies. And we had mechanical sounds like a shaver. So those 6 categories, air, mechanical, alarm, liquid, impact, and cyclic sounds, they are actually the categories that we talk about. And you will notice that an air conditioning sound, an air sound, or a hair dryer sound, they would be similar. And we will often make mistakes in identifying these sound objects if we don't see them. And because they are perceptually very, very similar. And many people will also make the same mistake between a shaver and a toothbrush sound, because they're also perceptually very, very similar. And similar mistakes are also done in alarm sounds, and this becomes a very big problem in the industry, in healthcare, in monitoring, very sensitive products or missions. But these categories, what we also did was to understand how people describe them. So for me, it's interesting to know how people attribute meaning to sounds. And we also found out that people use different associations for air sounds and to alarm sounds. For example, for alarm sounds, the abstract meaning of that sound. For example, if a microwave rings a bell, then we know that the food is ready. So that's the meaning that's very associated to it was important. But for a mechanical sound, source, identification of the source, whether it's a shaver or a toothbrush, was very important. And we found other descriptions. We have emotional reactions. Sound can be irritating to us, or they may be pleasant. Or we identify materials in the sound. We hear metal sounds, or we hear wood sounds. And we identify the duration of the sound. But sometimes we can't identify sounds, and we don't have any words to describe them, and therefore we imitate them, and we use onomatopoeia to describe what we heard. And if the identification is very secure when we listen to a sound, then we are very likely to identify the source. And if the identification is not secure, then people go into higher level categories such as abstract meanings and the action. They hear something is breaking, but they don't know what is breaking. So they may use more general terminology to describe. But there are, these categories are, descriptions are very stable as well. And when we listen to products, there's this time domain, and there are lots of little events. I want to invite you to listen to this coffee maker and try to find out what you heard in it while and imagine how we interact with the product. So we heard an on and off button. We heard some valves ticking because the pump has to push the water up. We heard boiler rustling. That's the heating element, right, for the water to be warm. Then we heard the pump whirring, and there's squeaking sound, which that was for example, a problem for us to solve as sound designers. You heard spraying, coffee flow, and finally the coffee is finished, and you hear an ending of a boiler rustling. So we are able to distinguish these different events, and thanks to our perception that all these lower, higher frequencies, loudness, intensity in the sound, they all gives us clues to understand what's happening in a sound event. And this is one of the last examples about how we listen to the sound. I want to play to you 3 different types of sound, because we did a study on how we can change the pleasantness. Can we improve the pleasantness, and what plays a factor? So what we did here is we did a low pass and a high pass filter for the frequencies of a shaver sound. And the idea is that when it is when the sound is lower, it will be more pleasant. When the sound is sharper, it will be less pleasant. So these are also the basics of psychoacoustics and sensory pleasantness. So this is the original sound. Now listen to this one and try to see if it is more pleasant or less pleasant. So this was a lower frequency sound, right? And here there was a higher frequency content, so it's supposed to be more unpleasant. And we are able to distinguish that, and listeners then say, I want a more pleasant sound, and then we know what they mean with that. So in general, let's summarize. There may be different responses to product sounds. So we may experience product sounds on a very basic sensory level. And so we may just listen to what is happening without knowing the source, or just without even interested of identifying what the source is. And we may say that sensory experience may be, I may like it or I may not like it. Because if there's no product identity attached, you may just refer to sensory pleasantness. For example, an espresso machine sound, if you just listen to them as sound, you may say, well, this is psychoacoustically not a very, very pleasant sound. But when you listen to the same espresso machine sound, and then you really need the coffee and you want it, you will never complain about that sound, and you accept it. So on a utilitarian level, the product itself has an effect of context, and it changes the way we appraise the sound, and we accept the sound, although it may be psychoacoustically unpleasant. And there may be a bigger contextual effect, the brand. If I, have a very expensive coffee maker, or if I'm influenced by George Clooney's advertisement for Nespresso, I may have an emotional experience with the coffee maker, and then I may say, well, I will go for Nespresso coffee maker because that coffee maker, I find it very pleasant, and etc. So there may be very different experiences, and every time the product interferes with the sound, it's going to change the way we perceive the sound. So, but how did we analyze these sounds? And I think there was this very traditional view on listeners being exposed to sound. Yes, we hear them. And then we did laboratory studies. Everything was considered noise. And we just measured, loudness or maybe the sharpness of the sound. And then, but we said that the listener is exposed to sound, so let's just measure it. And so that was kind of very traditional to do that. But after the 2000s, we had much knowledge about the experience of sounds. We realized that sound is an attachment to the product. It's sometimes subservient to the product experience, but sometimes, like in Harley Davidson, it can be very highlighted. So there is interaction and there is a user. We are not exposed. We have feelings. There is a context. And we started to do studies more contextually, and then the brand values also showed up, and things got a bit more complex and interesting, because then we started from sensation and we ended up in behavior change, because you may use sound also as part of the entire trajectory from perception to action. And that would be very more interesting than just measuring loudness levels, because people are exposed. And I want to move to soundscapes, because when I think of the universe and how we can sonify it, I can't help but think that there will be multiple different objects. So it is not just about sonifying every single planet or the stars, and but there is things are in constellations, right? They are together and they exist, they coexist, or there will always be other objects. So that means there will be multiple different sounds. And how are we going to think of that? So I think the notion of soundscape, that means that there is a listener that is interested in understanding this environment, and there are different sound objects, and there's actually sound that represents them. So that would really be interesting for us to see how not only one listener, but maybe different types of listeners interact with it. So then we talk about a very acoustically rich environment. And but I think then there needs to be really specific rules or guidelines to understand this environment. So there are lots of definitions of soundscapes, and I don't want to steal anyone's or step in the toes of others, but my definition is as follows. Soundscapes are the auditory representation of a complex function in a specific environment. They refer to highly rich sonic environments with multiple sound-producing events that have an ecological relevance, right? And there are actually active and passive listeners that have different relation to and different concerns with the sounds. I work with intensive care, and this active passive listeners is very, very specific there. A patient is a passive listener of alarms, but a nurse is an active listener of those alarms. And those alarms, and together with other healthcare devices, they create a soundscape, and those alarms have to stand out amongst the mechanical ventilators or alarms of other devices other than patient monitoring. A bat can also have an alarm. And so it's important to know who is listening and how much they are engaged with it. And when we look into soundscapes, it's also important that there are actually two components. There's a physicality to it, because it is a sound, it's a collection of sounds, but there's also the psychological construct of it, because someone has to perceive it, like Massimo explained to us. Someone has to go through that experience of that sonic environment. So when we look at the characteristics of soundscapes, just excuse me for a second. It's important that the function of that complex environment is well defined, because even when we sonify the space, what is it for? That's important. What is it going to allow us to understand? It's not just pure representation, but there must be a reason why engineers, astrophysicists are interested in it. And what type of sound producing events are there? I mean, can we categorize planets, and the stars are in a different category, comets are in a different category? I'm just, and what types of stars are we talking about? Are they far away or nearby? And it is important, this auditory quality, and which Massimo also explained at the end, right? There has to be distinct qualities to these different types of sound events so that our perception is not fooled, or it is supported with the right auditory representation. And from the listener's perspective, please do not forget that there are different sound cultures, and maybe Southern America will have a different sound culture than maybe people from India or people from Europe. We all grow up in different sound environments that shape the way we listen to the world. So there will be different ways that we interact with these sounds. We may look for very uniform ways of representing the sounds and understanding them, but we have to understand that we have to train for that. And there will be individual roles and experiences. A musician will have a completely different attitude, or a very experienced astronomer will have a different knowledge, and then they will look for other things. So it is important to acknowledge that. But that there are also different types of listening modes. We can listen to sounds musically, or we can listen to sounds object-based, and we will do the same with are we listening to planets, or are we listening to different timbres? And at some point, people, we have to also, I think, tap into those different types of listening modes. I just want to finish my presentation with two examples. As I said, that I mainly function in healthcare domain, and what we did here was we sonified patient vitals, heart rate, oxygen saturation, and respiratory rate. And the way we sonified was to create a musical piece, because we were very, very interested in the aesthetics of this sonification as well. And we thought such a sonification could allow us maybe to have a soundscape of an intensive care unit. So I will play this piece to you now. It's a little bit long, 30 seconds. I hope it's okay. So what you heard was actually different sound events and different instruments that would represent different functions. One would be for respiratory rate, and another one, like heart rate, was represented by drums, and oxygen saturation by guitar, blood pressure by piano. So by giving different objects, different timbres, we created this distinct description. But we also thought if we were to put this representation also in a sound domain, how would that look? And this is what we did. This is very distinct alarms. So this helped us also to help nurses listen to alarms in a different way, more pleasant, and to change also the soundscapes. So that was my presentation, and thank you. And I look forward to the questions that might arise, and maybe we see you on Tuesday.